Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at the tricky Fmbs 2008-2018 question. And the question reads, an electric motor operating with a voltage of 120 volts provides a mechanical power of 240 watts. This motor, which is crossed by a current of 2.5 ampere, has an EMF. So you are given options A, B, C, D, and E. So they want you to get the EMF in the motor when a current of 2.5 ampere crosses the motor. So option A was 300 volt, option B was 24 volt, option C was 96 volt, option D was 48 volt, and option E was none of the above. So let's move straight to our solution. So at this level, you should be able to recognize that the type of motor we are talking about in this question is a DC motor. Remember that we have two types of electric motors, the DC and the AC motor. A DC motor is one that uses DC input, and an AC motor is one that uses AC input. Since the value for the voltage was a constant voltage and not a sinusoidal voltage, then we can conclude that we are talking about a DC motor in this question. So, what is a DC motor? A DC motor is an electrical machine that converts electrical energy into mechanical energy. In a DC motor, the input electrical energy is the direct current which is transformed into the mechanical rotation. So in DC motors, we input some amount of electrical energy, generally using a battery, and the direct current produced by that battery is transformed to some mechanical rotation. And DC motors can be found in handheld fans, and they can also be found in hand drills. So recall that EMF is the maximum potential difference across a source of electrical energy when no current is flowing through it. For batteries, EMF is represented as epsilon and is given by epsilon equals V plus IR, where V is the potential difference across a resistant element when a current I flows through the circuit, and R is the internal resistance of the source PD, that is the battery, and I is the current supplied by the source of electrical energy or supplied by the battery. So now at this level, we are going to be obtaining the analytical expression for the EMF of a battery, and later on we are going to obtain the analytical expression for the EMF of a motor, and we are going to compare these two expressions. So if you have a battery connected to a circuit as such, where no resistance is connected to this circuit to draw a certain current from the battery, then the potential difference across the ends of this battery is maximum since no current flows through it. And this potential difference is called the EMF of the battery. So the EMF is the maximum potential difference across a battery when no current flows through the battery. So when no current is flowing in the circuit, the potential difference across the battery is maximum and is given by epsilon. So epsilon is the EMF of this battery when no current flows through it. So let us now connect a resistor to this circuit and expand this diagram and represent it with their respective circuit symbol. So this is the figure we are going to obtain when we expand our battery, that is, we bring out its EMF and its internal resistance, and we connect a resistor with resistance capital R in the circuit such that it draws a current I from this battery. So for us to be able to obtain the analytical expression for epsilon, we must draw a loop in the anti-clockwise direction, or you could choose to draw it in the clockwise direction, but in this case I've chosen to draw it in the anti-clockwise direction. After drawing the loop, we are going to apply Kirchhoff's voltage law, and we can be able to obtain the analytical expression for epsilon, that is the EMF of the battery. So if we apply Kirchhoff's voltage law, we obtain negative IR minus IR plus epsilon equals 0. So you notice that the current flowing through this resistor is in the same direction as our loop, and hence the PD drop across this resistor is negative IR. Also, the current flowing through the internal resistance little r is in the same direction as our loop, and hence the PD drop across the internal resistance R is negative IR. And for the EMF epsilon, the loop moves from the negative to the positive terminal, and hence we obtain positive epsilon at this level. And we equate all of these components to 0. So we have summed all the potential differences in this circuit. And we equate it to 0 according to Kirchhoff voltage law, which says that the sum of all the PT drops in a circuit must always be equal to 0. If we make epsilon subject of formula, we obtain epsilon to be equal to V plus IR, and this expression is known as the EMF of a battery. So now let us analyze the diagram showing the principle of operation of a DC motor. So if you observe this figure, you are going to notice two bar magnets, and in between those two bar magnets is a current carrying conductor. And this current carrying conductor has been fashioned such that it forms a rectangular loop, and it is placed in between the two bar magnets. It is not only placed in between the two bar magnets, but the current I. So this is the current I. So this current is I. You need to take note of that. This current is I, and here you can see already it has been represented as I. So a current I is flowing through this loop, and this current is created by a DC source, that is this battery you can see here. So these batteries produce a current I that flows through this loop, and you notice that the current flowing in the branch AB is opposite to the current flowing in the branch CD. Remember that current carrying conductors placed in magnetic fields experience a force. So the force on the branch AB is downward according to Fleming's left-hand rule, and the force on the branch CD is upward according to Fleming's left-hand rule. So these two forces are usually equal in magnitude but opposite in direction, and hence form a couple. Hence, there is some rotatory motion obtained when such a loop is placed in a magnetic field. This rotatory motion is the quantity that is usually being exploited and used in electric fans and used in hand drills and screwing machines. It's important to note that as this current flows through the loop, there is some amount of flux change that tends to induce an EMF in this coil as it keeps cutting across the coil. Remember that if a coil is placed in a magnetic field and a galvanometer connected across the coil, then some amount of current will be recorded. This is because magnetic fields tend to induce some amount of EMF and hence current in a coil being placed in that magnetic field. So there's some amount of EMF, we call it the back EMF, since it is produced such that it opposes the original EMF or the change producing it. We call that therefore the back EMF, and this back EMF is the quantity that was asked in our question for us to calculate. So we are going to look at how to obtain an expression for the back EMF of a motor. Specifically, the EMF for a motor is called the back EMF, while that for a battery is called the EMF simply. So at this level, we are going to be deriving the expression for the back EMF of a motor. So if this is a setup where a motor is connected across a battery, then we can obtain this setup when we bring in the physics of the motor into play. Remember that a motor has a back EMF epsilon and an internal resistance R. So by using Kirchhoff voltage law, we can be able to determine the analytical expression for epsilon. Notice that the voltage across the battery is V and the current it supplies is I. So from Kirchhoff voltage law, positive epsilon plus IR minus V is equals to 0, and we obtain epsilon to be equals to V minus IR. So if your loop is in the anti-clockwise direction as such, and your current flows in this direction, then we are going to notice that as this current flows through this resistance, it opposes the direction of it. So you notice that as this current flows through this resistance, that is through this internal resistance, it flows in opposite direction to our loop. Hence, the potential difference or the PT drop across this internal resistance is positive IR. Notice that our loop transits from the negative to the positive of epsilon, and hence we obtain positive epsilon, and across V it transits from the positive to the negative, and hence we have negative V at this level. And when you make epsilon subject of formula, you obtain epsilon to be equal to V minus RR. So this is a very important expression. This expression is very important. We are going to use it in solving many questions. And notice that this expression is opposed to the expression for the EMF of a battery. So EMF of a battery is equals to V plus, and not minus in this case, plus IR. So EB is equals to V plus IR. But for a motor, the EMF of a motor is equals to V minus IR. So we can now solve our question by using the derived expression for the back EMF. Remember that V was equals to 120 volt, P was equals to 240 watt, and I was equals to 2.5 ampere. All of these quantities were given in the question. So from epsilon, which is the back EMF, equals V minus IR, we obtain epsilon to be equals to 120 minus IR. We notice that we cannot continue our replacement since we are not given the quantity R. So notice that P is equals to I squared R, that is the power is equals to I squared R, and therefore making R subject of formula, we obtain P on I squared, and replacing R in the expression for epsilon, we are going to obtain epsilon to be equals to V minus IP on I squared, and hence epsilon is equals to V minus P on I. Therefore, replacing V by 120, P by 240, and I by 2.5, we obtain epsilon to be equals to 24 volt.